functions of several variables. Today I'm taking continuity of multiple variable calculus. For continuity, the analogy we always have is when you want to draw, let me change the pen from red to, I think blue should do. Oh yeah, blue. We always say we draw a circle. When you draw a circle, you don't lift the pen, and that's the idea of continuity. It is continuous. Now look at this approach. When I draw this circle and I end here, I have to lift the pen up. There's a gap here. It means this is not continuous. So mathematically, how do we define a continuity of a function? So assuming you have a function that defines the interior of a circle at any center A point AB, it says it's going to be continuous if the function is well defined in its domain. So it says it exists. If the limit of this function is also well defined, it means it exists. And then the last thing is to check that these two are equal. You always don't want to miss this out, please. You always want to check. But in a case where this does not exist, in the first case, the function does not exist, you don't have to even move to unit 2 or 3. But assume it exists, okay? But then the limit does not exist. You don't even have to move to the third one. Automatically, they are discontinuous. But in the case where they all exist, then you have to move to the third property and then check if they are equal. If they are equal, it is continuous. If they are not equal, it means they are discontinuous. So that is the preamble I have for you. So what is discontinuity? Discontinuity can happen when there's a hole in the function, when there's an upward change, or there's growth, power growth. So the first one is when there's a hole and there's a break. You can see it moved. It was from here, then it just jumped up. Okay, it can even jump down. So that's a jump. And here you can see there's a growth, one growing this way, the other growing that opposite in a parallel form. So mostly for the whole part, we say the limit does not exist, but in all the functions will be well defined. In all the first part will be well defined. In all three, they are well defined. But then the limit is when the issue starts. The limit does not exist here. The limit are not equal from both ends. So from negative point and positive end exist, all right. So this is why we use exist in mathematics, not the symbol, but they are not equal. All right. So note the differences. And here, the limit exists for both sides, but there's one is negative infinity, the other is positive infinity, and that is when you tell me as infinite discontinuity. So this is removable. This is a jump discontinuity, and there's infinite discontinuity. Just by the image you can tell. So let's take quick examples here. These are very simple examples. Example 1, you are given a function, you are given a point 5, negative 3, and you have to declassify this function. First, you must check if the function is well defined in the given point. That's the domain of the function. So what is the domain here? I just have to check that my x plus y plus 1 is not equal to 0. Or in other words, my y plus x is not equal to negative 1. So let's see, 5 plus negative 3. I'm going to get 2. 2 is not equal to negative 1. So it means that this point would give me something realistic. And I can do a direct substitution. Let me just show everything down for you as usual and then compare. If you do a substitution, you're going to get 3. Take a closer look at that for me. Okay. And then you find the limit now. The limit, there's a difference between the domain and then that of the limit. You've gone to limit of function, so you want to go back and play the video and then realize that the limit of this function, because I can do a direct substitution, is also going to be 3. Now the third one, since they all exist, this exists, this also exists, I have to move to the third option. Are they equal? Yes or no? Yes, they are equal. 3 is equal to 3, and hence it is continuous. As simple as that. Example 2, I have the square root of this. Okay, what will be the domain of this? The domain will be such that my 2x squared plus y squared should not be I think should not be greater than 26 to avoid the negative square root. That's assume I want to work in a raw line. You know negative exists. Negative of a square root is a complex root. Okay. So what is the domain here? Sorry, the function f of 2, 3. I can do a direct substitution and see. So let's see. 26 minus 2 times 4 minus 3, that's minus 9. If we check this out, that's 26 minus 248 minus 9. How this is correct? Okay, square. That is 32 minus 9. Use the calculator, you're going to get 3. And to find the limit of this, we want the limit of functions. You want to go back and then check that the answer here is 3. Now let's compare them. In comparative, they are all equal, and hence it is continuous. And that is it for the last example. Try the last example out, and then it is continuous. Why? Because I can do a direct substitution, and then I'll be good. Now to the ultimate thing is the problem of the day. So example 3, we've gone through that. It is continuous. Check why am I getting 21 in my slides. Now to the problem of the day. It says we want to go back to problem 1 where we're looking at average cost of production, and they want to consider the average cost function defined by the manufacturing firm for X economy and Y premium. Determine how smooth the firm changes in total cost of production. In problem 1, we have the average cost function as this. Okay, the total cost over the sum of productions you are making. So sum of production is X plus Y, and there's the total cost. But in problem 2, we are just considering the total cost, not the entire average cost. So it means our concentration is on the numerator here. How smooth is it? The smooth should tell you that what is the continuity. That's where continuity comes in. No limit, not limit, but continuity. But you know, continuity depends on limit of functions, and that's how interesting continuity is. So it's an application of the limit theorem. Okay, so what is the domain here? You realize that because it's a polynomial, the domain will be such that X and Y can be any numbers in the raw line, but they should be positive raw numbers because you're looking at production. So you can't have negative X. No, they should all be positive. So sometimes you must think smart to know, not just write the mathematics, but look at the preamble given and know what to do. They should be positive. If you write just R, you are wrong. Or someone would say they should be positive in integers. I think that one should do. So they are counting numbers. So production 1, production 2 for X, and so on. I think I prefer this one. Determine the smoothness of it. Someone will want to go through the continuity process. Find the domain, find the limits of the TC. So in place of X, I'm going to use TC of the point. Here realize that we don't have points given, but that from the domain it means that every point would work. Every point of X should give you something defined. You find the limits here when you are done, and then you compare. But you don't have to go through all these struggles because every number of or every point given in this will give you a particular answer for TC irrespective of the X and Y you choose. You can choose points and then just check. You realize that we expect that there will be from gadget 2, 3 to gadget 4, 5. The difference will not be so much. So there is smoothness in the changes as you increase production, kind of. So assuming I have a graph here, and then I have X and then Y here. The small change in X and Y should not be so much that when it gets here, it just shoots and then start from somewhere. This is the discontinuity aspect. But how smooth it is, you want to make sure that if I change X and Y point, the changes in my total cost should not be so much different, and that's how smooth it is. This is very important because the company wants to check their selling price, want to check their production level, and then the cost efficiency between these two gadgets. That's how continuity is very important in our firm for production. Thank you very much for staying with me. And the next one is going to be on partial derivatives. So take your time and go through that for me as well. Thank you.